First week, it's big picture motivation. We're interested in legged mobility, and we're going to be trying to give you some sense of that as an emerging area, still not well understood area of robotics. There's increasing commercial activity. Here's a movie of the Ghost Robotics Company product, which is a spin-off from my lab. Go to their website and see if you want to buy one of their machines. I'm trying to get across the idea that these commercial endeavors are still very, very, very new. We're still very far from understanding the depths of the foundations. But we're going to focus on, in this first week, on trying to give you some sense of what we mean by the foundations. And the foundations include principled bioinspiration in a way that we'll try to explain, understanding the basic physics and math and the new math that's come out of the physics. And then we're going to try to develop an emerging engineering theory and apply that theory to successively more realistic simulation models of machines that actually exist in the physical world and that may someday soon be commercial, such as this Jerboa machine that Avik Dey is programming as part of his thesis research at University of Pennsylvania. And you'll be doing a project in week 12 on the Jerboa machine. More on that soon. Week 2, we're going to start you with the very, very, very basics, things that we're assuming that most of you already know. It's part of the prerequisites to understand the basics of ODE theory and linear algebra, such as would help you understand the Physics 101 first-year college physics course on linear spring mass dampers. Only we're going to take a dynamical systems spin on these systems that we hope you already are somewhat familiar with. We're going to interpret the accelerations and the forces as sources of vector fields, and we're going to be thinking about the integral properties of those fields as flows and introducing what we mean by that. We'll be introducing qualitative notions such as change of coordinates and qualitative ideas that are descended from physics, ideas such as energy, power, and basins that started out being physical notions but needed to get generalized by the mathematicians for us to find them useful in our construction of aphysical new robot behaviors. Week 3 will continue our fast and furious paced review of what you used to know. Even if you learned about linear dynamical systems in Physics 101, possibly you never really learned about nonlinear physics, such as animates these pendula, your grandfather clock, or the spinning legs of a robot, even one leg of a robot. And here we're going to revisit the notions of energy from the week 2, and we're going to realize that we have to start thinking much, much more qualitatively. You have to think about conservation laws. We have to think about qualitative theory, such as dissipation of energy, and eventually we'll call that stability theory. Stability theory then gives rise to the kinds of topological ideas that we're going to be moving toward by the end of the course. Well, week 4, we're going to take a deep breath and we'll say, okay, enough theory, enough math, enough physics for a while. Let's just put these things to use. And we'll use the example of this ape-inspired robot that my colleague Toshi Fukuda, professor at Nagoya University in Japan at the time, he and his graduate student were interested in building machines that could swing from the trees from branch to branch the way the apes can. Well, we're using that in week 4 to give you some feeling as to how complicated even these 2-degree freedom revolute dynamics are. And in this GIF, you can get a sense of how chaos is actually built into these 2-degree freedom systems. Until and unless, even with one actuator, you can get the robot to impose forces over time in a pretty simple way, such that you can see the bottom swinging 2-degree freedom thing, which only had one actuator, doesn't have 2 actuators. It is going to swing from branch to branch in a very controlled and pretty well understandable way because of these energy basin kinds of ideas that we're starting to expose you to, even in weeks 2 and weeks 3, and we'll spend a lot more time in the future weeks. Week 5, we're going to plunge back into dynamical systems theory, and it's the most mathematical part of the course, and we'll get through it and you will get on with the engineering life. But we've got to do a little bit of normal form theory, which starts with Taylor series that you knew from calculus, advanced calculus, but uses Taylor series to introduce what are called normal forms, first when you're away from an equilibrium state, and then when you're close to an equilibrium state, we have to introduce these ideas of hyperbolicity, where you have what are called structural stability properties, means that you're not going to be too vulnerable to changes in the models. Small changes in the models won't change the qualitative properties of the behaviors that we're building. And they're very, very careful mathematical ideas that got developed in the 20th century as generalization of the physicist notions from the 19th century. Crucial among these is the notion of linearization near a fixed point, where you're going to be using linear algebra and matrix calculus to get conclusions, qualitative conclusions, rigorous qualitative conclusions from computationally effective, simple calculus manipulations. Those generalize into global conclusions, not just properties that are close to those fixed points or equilibrium behaviors, gates, limit cycles, but far away. Now, we won't have too much opportunity to do the global property for which we need Lyapunov theory, but we're going to introduce it as a generalized energy, and we're going to reintroduce it as a metric that you learned from possibly linear algebra. And generalized power is going to be reinterpreted as a stability criterion. All right, that's week 5. It's the most mathematical part of the course. I hope we've made it accessible, and I hope we'll be able to show you how these crucial ideas get applied later on in the semester. Okay, week 6, we're going to introduce our first arguably locomotion model, and we're going to be dealing with Raybert's brilliant dynamical running work from the mid-80s. I think that Raybert was the most important roboticist of the 20th century. And core to his ideas was this vertical heartbeat. And so we're going to use the vertical component of the Raybert hoppers to introduce and apply all the ideas of the preceding weeks to a very fundamentally new setting that shows up in locomotion. We're going to be developing vector field and flow models for each mode. And what I mean by a mode is sometimes you're in stance and sometimes you're in flight if you're going to be doing dynamical locomotion. And so we have to derive flows for each mode. And then in week 7, we have to encounter a completely new object that wasn't known to the physicists, really, that was not even known to the 20th century mathematicians, that the engineers have brought to the mathematicians' attention. And these are hybrid dynamical systems. We're going to reinterpret the Raybert vertical hopper as a hybrid dynamical system, meaning, as you see in this GIF that Wei-Shi Chen, one of our wonderful TAs, has prepared for us, you can see that we have an alternation of flight to stance and flight to stance, and sometimes the spring is engaged and sometimes it's not engaged, sometimes we're thrusting, sometimes we're not. This is a hybrid dynamical system where we have different contact modes and we have transitions between them, and we have to account for these things in a very, very methodical way so that we can derive the so-called Poincare map, or the return map, which is going to express the state of the next hop as a function of the state at the previous hop. And that function will become our model of the gate. And the stability of that gate will require that we learn a little bit of fixed point analysis for these discrete time return maps, where, again, in discrete time, we do the same kind of linearization that we taught you how to do in weeks 2, 3, 5 on continuous time. We do that linearized analysis, and in this setting, in the Raybert vertical hopper, we're going to discover how to a priori understand where and when the gains of the Raybert controller will work and when they won't work. And we'll introduce some ideas about what might go wrong and why it might go wrong by using this analytical point of view. Well, week 8, okay, we'll take another breath and we'll say time to do some more projects. And project number 2 at week 8 is just your chance to play around numerically with models that lead up to the Raybert vertical hopper, but very much strongly depend upon the notion of a hybrid dynamical system. So Wei-Shi is going to give you the opportunity to use all the theoretical ideas that were developed so far, starting with a very, very simple physical setting and increasing mechanical complexity that begin to approach the complexity of the later weeks, where we want to actually look at numerical models of physical machines. Okay, so Wei-Shi will start with a bouncing ball model. He'll take you through a Raybert vertical hopper model, and then he'll introduce a much more complicated machine, still just in the vertical degree of freedom, but this machine will have motors, it'll have linkages, and the job for this machine will be to anchor the Raybert vertical hopper, which is just trying to be a bouncing ball. And so that's what week 8 is all about. Week 9, we'll return to the simplest of the running models, which is the spring-loaded inverted pendulum. Now we'll be thinking about animals as pogo sticks, because that's what the bioinspiration tells us. And when we start thinking about pogo sticks, as the animals insist we must, we run into a fundamental problem, which is that we needed the Poincaré map, which is our discrete time stride by stride control model, but that stride by stride control model actually is the integral of the within stride continuous time model, and that entails closed form flows. But the mathematicians tell us that when you look carefully at pogo sticks, you get coupled nonlinear 2-degree freedom systems. And Poincaré showed in the turn of the last century that these 2-degree of freedom, even these 3-body problems, which become 2-degree of freedom systems when you look at them, are formally non-integrable. It's not just that we're too stupid to get their closed form expressions. You can't, mathematically, you can't integrate them. So the way forward in week 9, we'll discover, is to introduce an approximation by getting cyclic coordinates, and that gives us 2 conserved quantities when we take the Hamiltonian point of view, which takes some doing. That's what we're going to be doing in week 9. It'll give us the opportunity to get these closed form expressions to give us at least an expression of the plant model, the control plant model, in the stride-by-stride sense. And that's what we're doing in week 9. That is going to seem a little tough to those of you who haven't seen some of these mathematical ideas before. Please, please, please fasten your seatbelt. I hope we're making it accessible to you, and I hope the exercises and the labs that we're developing are going to help you get through. These are not easy ideas, but they are essential to principled engineering approaches to legged mobility, as I hope will come to convince you. Week 10, we're finally able to use those hard-won models. We're going to simplify those hard-won models still further by introducing yet other ideas from mathematization of the physics of the 19th century. We're going to exploit conservation laws, sure, but we're going to introduce and we're going to formalize Raybert's brilliant insight that symmetry is at work here, that what the animals are really doing is they're benefiting from symmetry. We'll explain Raybert's ideas about symmetry, and we'll introduce the more formal mathematicians' rendering of what that symmetry means, beautiful ideas that they are. But we're not mathematicians, right? We're engineers. We're going to take these ideas and we're going to use them. We're going to use these simplified, symmetrized, approximate conservation law-based representations of the fore-aft component of the slip return map. We're going to use our ability to do closed form analysis to get a linearized stepping model fixed point stability analysis. That's what we're doing in week 10. And why do we do that? We do that so that we can then analyze the Raybert stepping model from his brilliant work in the 80s, show you how it works, why it works, and show you when it's not going to work maybe, and then suggest potentially more aggressive, faster transient strategies that use model-based in a way that Raybert couldn't because he didn't have the models available to him as alternative stepping laws. And we'll compare and contrast and say, you know, often the Raybert law is the thing that you want to use because it's much more robust than these aggressively model-based rules, but at least you're now able to compare and contrast because you understand why the brilliant Raybert strategy is working. And so that's what we're going to be doing in week 10. Week 11, it's time to use these ideas in still simple models where we take you, and here Vassiliopoulos, our wonderful TA, is going to be taking you from the full 2-degree of freedom spring-loaded inverted pendulum model that combines the vertical height loop that we did in week 7 and you did in your project in week 8, and combines with that the stepping, 4 aft stepping loops that you did in weeks 9 and 10. Okay, and so now in week 11, we'll be introducing far more realistic running bodies with many, many more degrees of freedom, and we'll be actually starting to add appendages such as tails that begin to sneak you up on the kind of jerboa physical model that Avik is working with in his thesis, and that we hope for you to work on in week 12. And that's what we're doing in week 12. It's the last project. It's a project on the jerboa robot, where what we hope to do is we hope to give you a pretty good numerical study of some of the aspects of this jerboa. Well, not all the beautiful aspects that Avik is showing off in these movies here from some of the papers that he's been writing recently. You know, the jerboa is this 12 degree of freedom, very complicated physical machine. It only has 4 motors because, remember, each time you add a motor, you decrease your specific power. You add watts, but you lose watts per kilogram, right? And so this jerboa was designed to be not so straightforward, but designed to explore parallel composition in a very highly capable, agile body that has a lot of specific power because it has so few actuators, but actuators that are highly placed to exploit dynamic coupling, okay? And so we're going to try to give you some sense. I mean, this is a robot at the very cutting edge of what we understand. We understand something about it, but we don't understand too much about it. Certainly, we don't understand a lot of the transitional behaviors that Avik and his collaborators are getting out of it. So it's the cutting edge of contemporary legged locomotion research, but I'm arguing to you that you can do this project in week 12, partly because my TAs are so skilled in making these things accessible to you, and partly because we've tried to give you some of the fundamental ideas that make accessible the generalizations of these simple ideas, beautiful ideas that pioneers like Raybert introduced to us in the late 20th century, and that it's our job to use and explore and generalize and exploit in the years to come in the application of robotics to ground mobility and locomotion engineering. Welcome to the course Robo4, the last course in the mini masters series for the University of Pennsylvania robot series.